So how do we actually hand over the keys to our most critical networks to an AI without, losing control? That's the huge challenge we're going to tackle today. We're going to explore a framework that's all about building real trust and, most importantly, putting a human safety switch on these incredibly powerful AI tools.
And that brings us to the fundamental question, right? Just because an AI can do something, does that mean we should just let it? I mean, especially when we're talking about the digital arteries of our organizations, the network infrastructure itself, how much autonomy is really okay and how much is way too much?
Well, to even begin to answer that, you've got to realize that AI autonomy isn't just a simple on or off switch. It's really a whole spectrum of human involvement, and we're about to walk through the key models on that spectrum right now. Okay, so on one end of the spectrum, you have the most supervised model there is, human in the loop, or HITL. The easiest way to think about this is like an AI that flags a potential issue on a medical scan. The system literally stops and waits for a human radiologist to look at it and make the final call. The AI recommends, but a human has to approve before anything happens. Now, in the middle, we've got human on the loop. In this case, the AI is operating on its own, but there's a human actively monitoring, ready to jump in and take over at any second. Think of a modern pilot with an autopilot system. The plane is flying itself, but the pilot is right there, hands near the controls, ready to take over if something looks off.
And then you get to the far end of the spectrum, full autonomy, human out of the loop. Here, the AI senses, decides, and acts completely on its own, and it often does it at speeds where a human couldn't possibly intervene anyway. The classic example is high-frequency stock trading algorithms that can execute thousands of trades before a person could even blink.
Okay, so we've got this spectrum, but how in the world do we decide where a specific task should fall? And that, right there, brings us to the biggest challenge of all, what I call the trust calibration problem. How do you learn to trust an AI when you know for a fact that it isn't perfect? See, here's the thing you have to remember about AI. It's all about probabilities, not certainties. It'll say something like, I am 92% sure this is a threat. Well, that immediately creates that classic signal versus noise problem. How do you stop your team from chasing digital ghosts all day and getting totally burned out by false positives? So how do we filter out all that noise? Well, smart engineers use three pretty clever techniques. First up is sensitivity tuning. You can literally dial the AI's sensitivity up or down depending on how critical that part of the network is. Second is contextual suppression. You teach the AI to just ignore alerts during, say, a scheduled maintenance window. And third, and this one's really smart, is peer validation. If one user reports slow Wi-Fi, but 50 others in the same area are totally fine, the AI knows it's probably an isolated issue, not some huge network meltdown. All of this brings us to the absolute core of our framework, the human safety switch. This is a model designed to make sure that the network engineer's expertise, their gut feeling, remains the final authority, no matter how clever the AI gets. You see, trust isn't something you just get by hoping the AI is right. It's built through something called explainable AI, or XAI. A black box system that just spits out a command like, fix this, is worse than useless. It's dangerous. But an AI that provides the hard evidence behind its recommendation, now that is a partner you can work with. And hey, this isn't just some vague concept I'm talking about. The National Institute of Standards and Technology, that's NIST, has actually defined a brilliant framework for this, and it's all built on 4 core principles that any AI partner worth its salt absolutely has to follow. The first principle is simple, but it is absolutely essential: explanation. The system has to give you the why. It must deliver the evidence, the data, the reasoning for its conclusions. Bottom line, no evidence, no trust. Second, that explanation has to be meaningful. I mean, a wall of code might be a technically correct explanation for a developer, but it's completely useless to a manager who needs to make a business decision. The system has to provide explanations that are actually understandable to the person looking at them. It's a huge design challenge, really, creating an AI that can speak multiple languages depending on who it's talking to. The third principle is explanation accuracy. And this is so important. The explanation the AI gives you can't just be a simplified story that sounds good. It has to be a true and accurate reflection of the AI's actual logic for how it got to its conclusion. This stops the AI from dumbing down its reasoning to the point where it becomes misleading. And finally, the fourth principle is knowledge limits. Honestly, this might be the most important one for safety. The AI has to be able to say, I don't know. It has to recognize when a situation is totally outside its expertise, or when its confidence level is just too low to make a call. Building an AI that is self-aware of its own limits, that's one of the hardest parts of creating a truly safe system. So, what does this actually look like in the real world? Well, instead of a simple good or bad alert, a trustworthy AI gives you something you can work with, a quantifiable trust score. So here, we see a score of 6 out of 10 for a device. That's not a full-blown panic, but it's definitely not perfect. So the obvious question is, why a 6? And because the AI provides the evidence, it tells you exactly why, tying directly back to those NIST principles. The trust score is a 6 because 1, it's detected the same unique device ID, the MAC address, in 2 places at once, which is weird. 2, it also found weak credentials on the device itself. And 3, it's using a less secure authentication method. Each point is a specific, actionable insight. The engineer isn't guessing anymore, they're informed. This brings us to the final, and I mean the absolute most critical layer of oversight, the kill switch protocol. This is the procedure for when the stakes are at their absolute highest. We can pretty much categorize all AI actions into 2 big buckets. Over on the left, you have autonomous actions. These are low-risk tasks, things like opening a support ticket or collecting some diagnostic data. They don't break anything, so yeah, we can let the AI handle those. But over on the right, we have the augmented actions. These are the big ones, the high-risk changes that could cause a massive outage. We're talking about things like shutting down a major internet connection or changing a core firewall rule that protects your crown jewels. For these, we need a totally different approach.
And for those high-risk actions, the rule is absolute. The AI provides the insight, it shows you all the evidence, it gives you the recommendation, it does all the heavy lifting and diagnosis. But the network engineer, the human expert, must be the one to click approve. This is the non-negotiable final safety switch.
Look, at the end of the day, AI isn't here to replace the network engineer. It's here to be the most powerful co-pilot you've ever had, one that can see everything, analyze everything, and recommend the best course of action in seconds. But make no mistake, you are still the captain. The final command authority always rests with you.